When getting into more complex molecules, we have to have an understanding of formal charge. And basically, this is the charge, on an atom, basically as a result of, its valence electrons, lone pair electrons, and bonding electrons. And, there's an equation for it, that formal charge would be equal to the number of valence electrons minus the sum of the number of lone pair electrons plus 1/2 the number of bonding electrons. So that's our calculation for formal charge. Before we get into some of the rules, let's just do a simple example of it with CH3F. So reinforcing what we've learned already with these types of simple Lewis dot structures, right? We have 3 of our hydrogens, each one with 1 valence electron. We have a fluorine with 7, but similar to hydrogen, it just has that 1 unpaired valence electron. And then we have our carbon atom. So just remember our rules here. We only have basically 1 valence electron to share. Right, that's why these go on the outside of the molecule. And then with our carbon, we have the most unpaired valence electrons, and that's why it's going in the middle. So we can develop a structure, hopefully now getting a little bit easier here, with our carbon in the middle. We have our hydrogens, and then our fluorine atom. If you look at each one of them, right, our hydrogens all have that noble gas configuration because they all look like helium. Our fluorine as well looks like our neon, and our carbon in the middle as well looks like neon. Again, that noble gas electronic configuration is why, right, our structure would look something like this. Now to bring the idea of formal charge into this, we could say, for these formal charges, we can start with our hydrogen. They actually all are really the same with the hydrogen, right? We're looking for, okay, remember our equation, formal charge equals number of valence electrons minus, right, our sum of bonding and lone pairs, right? So we have lone pair electrons plus then 1/2 our bonding electrons. So for our hydrogen has one valence electron. If we go into the brackets, it has no electrons as lone pairs. And then in terms of a bond, it has one bond, which is a sharing of 2 electrons, and we get a formal charge for the hydrogen equal to 0. If we go to our fluorine, we find fluorine has 7 valence electrons. It has 1, 2, 3, 4, 5, 6 electrons in lone pairs. And then it just has one bond or a sharing of 2 electrons. So we essentially get 7 minus 7, or again, 0 for our formal charge. And then lastly, we have the carbon. Carbon has 4 valence electrons. There are 0 electrons in lone pairs. And it has 1, 2, 3, 4, 5, 6, 7, 8 electrons involved in bonding. And we also get a 0 formal charge for the carbon. And that's really kind of what we want, right, in terms of getting to, some of the rules that we have here. Right, and realize that elements really like to have the lowest formal charge possible when we're part of a molecule. If an element uses all its unpaired valence electrons, in bonding, then its formal charge is always equal to 0. And that's the big important feature that I've been trying to describe slowly through this piece, is that elements like to share their unpaired valence electrons. That's what they like to do. And a reason behind that is because that means that they will have the lowest formal charge possible. If an element uses all of its valence electrons, in terms of those valence electrons being unpaired, then it always has that 0 formal charge. You can go through the calculation many, many times, but you always will come back to that same realization that, oh, it's actually 0 if I use the unpaired valence electrons. So that's an example of calculating it. Just as far as some rules that are involved. The first rule is the sum of all the formal charges must equal the charge on the molecule. So if neutral molecule then all formal charges sum up to 0. Second rule is that small formal charges, basically are better than large formal charges. Zero, +1, -1 are common. -2, +2, -3, +3, etc., right, are not common. So we really want to kind of fixate on these types of formal charges when putting together an actual molecule. And lastly, the most electronegative element basically should have the negative formal charge. Basically, if there is, a negative charge. So those are some of the rules that we find with our formal charge, is that we have, small formal charge is what we want. To be honest, neutral is really what we want. That's what happens actually quite often, is that we have, 0 for the formal charge of an element within a molecule. And again, that goes back to the idea that if the element is sharing its unpaired valence electrons, it's leading to that neutral formal charge state. And that's a big driving force, because ultimately that leads them to the octet, right? That leads them to that stable noble gas electronic configuration. If we do have formal charge, well, then we want to have the smallest formal charge possible, meaning technically really just like +1, -1. That's what we tend to see. There are, some other examples. There is some gray out there. But for us, if you are finding that elements in your molecules have formal charges like +2, -2, or greater, then there's actually a better structure you can put together with a lower reduced formal charge. And then lastly, in terms of periodic trends that we've talked about in a recent lecture, right, the most electronegative element should have that negative formal charge when we have, some type of discrepancy. So that's the idea between this notion of putting together a molecule in the Lewis dot sense, and then assigning formal charge to realize that maybe, okay, one representation is better than an actual, another. So let's look maybe at an example to try to, highlight that idea. This is an example that we've already actually done. We've already actually done carbon dioxide, but And I and I think that if you're following my instructions on how to put these molecules together, you won't run into this issue. But then again, maybe you're not listening to everything I'm saying and you're getting your information from other sources, and it leads you astray. So for instance, for carbon dioxide, we could actually put two different structures together, looking at this sense of sharing of electrons, right? Each oxygen element, right, having 6 electrons in its valence shell, 2 of which are unpaired, and then for the carbon atom having the 4 unpaired valence electrons. And we put that pretty much together, simply in saying that, okay, well, that means our carbon must be in the middle, and I must, be sharing those 2 electrons to 1 oxygen that are unpaired, and the same goes for the oxygen that is unpaired. And that led us to this structure for carbon dioxide. If we were to calculate the formal charge on each one of these elements within CO2, I can already tell you that it's 0, because I know that the oxygen used its unpaired valence electrons in both cases, and I know the carbon used all of its unpaired valence electrons as well. But we can still do the exercise. Meaning oxygen has 6 valence electrons, minus it has 4 in lone pairs, and it has a double bond, or 4 electrons being shared, and my oxygen formal charge is 0 based on that idea. And both oxygens are exactly the same. We can do the same thing with the carbon to say that, well, it has 4 valence electrons, no lone pair electrons, and it has actually 8 electrons being shared in bonds, and as well a 0 formal charge. So here we see minimization of formal charge. But you might find that you run into problems. Like, what if you just so happen to draw the structure, I'm not sure why, but like this? If you count up the number of electrons, it actually has the same number of electrons. We have 6 from each oxygen, so that's 12, and then 4 from the carbon, that's 16. And so what we see on the left also has 16 electrons compared to what we have on the right. Now, we should see some serious problems. Right? Carbon, there is no octet, right? And that should be really a driving force for us to understand that, okay, this structure is not correct. If you were to draw it according to now showing the bonds, we would end up with something that looks like this. If I calculate the same idea of formal charge for my oxygen, we find that each oxygen is actually going to have a -1 charge. That's because each oxygen has 6 valence electrons. Each oxygen has now 6 lone pairs of electrons. And each oxygen has 1 bond, which incorporates 2 electrons. So if we do that math, we end up with a formal charge equal 2 minus 1. If we do the same thing for the carbon, find carbon still has 4 valence electrons, no lone pairs, and it has 1/2 the number of 4 bonds, 2 bonds, 4 electrons in each. That gives us a charge of +2. And I apologize, I just corrected those equations that I had there. We need to have, a sum within the brackets. Full transparency, just highlighting that aspect to get to these formal charge values. So this means that this is correct. Each element using its lone pair, using its unpaired valence electrons results in, basically a neutral molecule where all elements have a neutral formal charge. That couples with the other side of the story where this is now incorrect. Each element has basically lost or gained electrons to bond. Still a neutral molecule if we consider it, right? If we consider the charges that we have. Right, this is still neutral. But, we have an excess of formal charge. And so if we go back to the structures at the very kind of top here, right, we find that, this molecule is neutral, right? Each one of the oxygens has, 0 for that formal charge for the oxygens and the carbon. If we look at the other version of carbon monoxide that we drew, which is really incorrect, right? We really have a -1 for the oxygens, and we actually have a +2 for the carbon. So there's that excess of formal charge. And so because of that, that idea of formal charge is basically why our first structure is correct. Looking at that carbon dioxide structure. Now, sometimes we already have a charge in the molecule, and so now, that brings some more formal charge implication into the mix. When we have neutral molecules, Not all the time, but a good chunk of the time, these elements are using their unpaired valence electrons, and all the elements in the molecule are neutral. Yes, there is a little bit of gray out there, but that's a good rule to kind of keep with in going forward. Let's do another example. So now we finally have a molecule that's actually charged, NH4 plus 1. And so charge on a molecule means you need to remove an electron. That would be a minus type of charge. Or, I apologize, that would be a positive type of charge because you're removing an electron. Or you basically need to add an electron. And that's where we might have a -1 charge. So that's what that +1, -1, or this idea of charge is doing, is we need to add electrons or remove electrons. So if we look at the two elements here, right, we have our 4 hydrogens. Each one has 1 electron in its valence shell. And then we have our nitrogen with its 5 electrons in its valence shell. And if we put that together, at least for the first 3, it's pretty straightforward. We end up with something that looks like this. But we still have a hydrogen actually left over. And so, how to basically incorporate in the molecule could be, a legitimate question. Well, what we see here in terms of our NH3, this is actually neutral. We have, basically not invoked charge. So we could go, one step further here to show that removal of an electron, meaning that we still have our hydrogen, and now if we draw in our component hydrogens from the NH3, I'm just going to go up a little bit here. Right, I'm going to remove one of those electrons, right? For that idea of the +1 charge, that I have to remove an electron. And as soon as I do that removal of an electron, I know that my nitrogen is +1 in terms of charge. What does that help me do? Well, now that actually helps me to put the molecule together, right? Because before I didn't have another unpaired valence electron to make this last bond to the remaining hydrogen atom. But the fact that this molecule is +1 means, okay, well, I need to remove an electron. If I remove that from the nitrogen atom, now that I do have the ability to actually put together the molecule, right, as far as all of its components. So now I can put the final hydrogen on. If we look, everything is still very happy in the sense that all of our hydrogen atoms have that helium noble gas configuration, and our nitrogen in the middle as well has that neon noble gas electronic configuration. But in the process of doing that, that means that that nitrogen is actually +1. So I can put the structure together. That looks like this, where I have my sharing of 2 electrons, creating my 4 bonds to the nitrogen. But my nitrogen is actually +1 charged. And we can do that via that combination of formal charge. If we look at the formal charges of our hydrogen atoms, each one has 1 valence electron, no lone pairs, and 1 bond or sharing of 2 electrons. And so that's where the 0 formal charge comes for the hydrogen. And for our nitrogen, here's where we would find things a little bit different now. We have basically no lone pairs. We have 4 bonds or a sharing of 8 electrons, and we actually end up with a +1 formal charge. And it's that +1 formal charge that we're representing there with the nitrogen. You can do the formal charge calculation, but what I like to do is just realize what we did up above. Sorry for the scroll back. But we realized in the top right-hand corner that we needed to make another bond to hydrogen, yet we couldn't with the nitrogen's electronic configuration. Because the molecule is +1, that means we can remove an electron. And so here is the point where, okay, that means I need to remove that electron from the nitrogen, because that allows me now to make the connectivity with all the atoms within the molecule. All the hydrogens now can bond to the nitrogen. And as a result, that's really where that +1 formal charge came from, the fact that we actually took it away from the nitrogen. So there's a lesson there. If I'm taking away an electron, that's going to result in a positive formal charge. Or, contrary, if I'm adding an electron to an element, that would now start to constitute a negative formal charge. But we can also calculate it like we see at the bottom. To be honest, I do not like the calculation. I think with enough practice of putting these molecules together, using this method as I've described, you will find that you actually know the formal charge at the very end of the day. If you're just sharing unpaired valence electrons, it's always 0. If you're pulling an electron, it's always positive. If you're giving an electron, it's always negative. Let's do one more example of that with hydroxide. Hydroxide has a -1 charge. So if we look at our oxygen, we would have our 6 valence electrons, and then we also have our hydrogen atom. In putting this together, right, we can easily make the one simple bond to the hydrogen atom, but we find that we're still lacking in terms of that oxygen. Right? Oxygen is, most electronegative here. So should get a negative charge, which we need, right, realize that we have to add an electron. So that means we have oxygen now with accepting an electron to make hydroxide. And because it accepted that electron, I can say that that oxygen is actually -1. And we'll find that that's a really good rule, that when we have a negative charge, we tend to add it to an oxygen within an element. Right, so, and that's a rule that we'll kind of keep, we'll definitely reinforce, is that it just so happens that when we tend to see there is a negative charge in the molecule and oxygen there in the molecule as well, well, it's that oxygen element that's going to get the negative charge, get the extra electron, because oxygen really is, one of the most electronegative elements out there. It actually is the most electronegative element out there that can participate in a covalent bond and still actually accept an extra electron. So we see that motif happen quite a bit with OH. So that's the idea of formal charge, and we'll keep reinforcing that idea in formal charge as we get into some more complex molecules in subsequent lectures. If we were to calculate the formal charge for each one of the elements above the hydroxide, right, our formal charge for the hydrogen would be 1 valence electron minus lone pairs plus 1/2 2 electrons being shared in the bond, and so we get the neutral formal charge for the hydrogen, as we would expect because we're using unpaired valence electrons. And then if we look at calculating the formal charge for the oxygen, we would start with 6 in its valence shell. It has 6 electrons as lone pairs, and it also has 1 bond with 2 electrons. And so notice that we get now a -1 formal charge. And that both of these sum up to have the the -1 charge on the hydroxide. But again, we already knew that in scrolling back because we gave that extra electron to the oxygen and made it negative. So we can do the formal charge calculation, but if you're careful about these electrons and whether you're giving them to an element or taking them away from an element, right? That's automatically now telling you formal charge if you keep if you keep track of that. Now let's talk about just a little bit more specifics into covalent bonding or covalent bonds. In terms of bond dipoles or dipole moments, as they're sometimes called. Bond strength and bond length. So 3 topics here. So first, let's get into the idea of a bond dipole. A bond dipole, like I was saying above, also known as a dipole moment, results basically in a covalent bond that is basically connecting two different elements of different electronegativity. Right, so even though the electrons in the covalent bond are being shared, they are not being shared equally. Right, and that goes back to that notion of electronegativity and an element's inherent desire to get electrons or pull electrons towards it. So if we were to look at elements such as, or molecules such as CH3F, and if we're a little bit faster now in putting together those simple Lewis dot structures, we would get something that looks like this. And what we find here is a bond dipole. Fluorine is, much more electronegative than the carbon. So we could draw that a little bit differently to try to highlight that idea of the bond dipole. By showing this idea that, okay, we have a partial positive charge and we have a partial negative charge. And the partial negative is on the more electronegative, while our delta plus, the partial positive, is basically on the less electronegative. Sometimes they also show this in terms of an arrow. Where we have our positive part of the carbon and showing which way the electrons are being pulled. So we have kind of two representations, if you will, the partial idea with the partial negative, partial positive, as well as then this idea of an arrow from positive to negative. So that's the notion that we have with this idea of bond dipoles, meaning that it's not a hippy-dippy equal sharing of electrons. It really is, electrons are held closer to the electronegative side, or the more electronegative elements. For our purposes, carbon and hydrogen are the only two different elements with the same, they're not exactly the same, but we can say with the same or similar electronegativities. And so that's really kind of talking about the stretch that we have between, covalent bonding and ionic bonding. Covalent bonding is a sharing of electrons, right? While ionic is not. And so we have to realize that there's lots of different, thresholds in that bonding scenario. With bonding, we can have that idea of, a pure covalent or pure sharing. We now can have this idea of a bond dipole, which is still covalent. So this would be equal, this would be unequal, but both of these are still technically sharing of electrons. And then we have ionic, which is, now fully charged plus and fully charged minus. So we have, all these are talking about really the same thing, in that we're talking about bonding. It's really just a question of how different are the electronegativities, right, in terms of what type of bonding system we would create. For, our pure covalent, right, we could look at oxygen. Right, this is the same elements on either side. So same electronegativity. This is a pure covalent bond with equal sharing of those bonding electrons. We go to, like a bond dipole, and that was one that we were just, talking about, but let's just do a different example of that. We could look at CO2, where we have our oxygens on either side of the carbon. But here we have a dipole, right? Our carbon is positive relative to our oxygen. And that's really on, both sides of that carbon. So here we have, an unequal sharing of electrons. But they are still shared, so still covalent. And then if we get into our ionic, systems such as, sodium chloride. Where now we're, showing that those electrons are not being shared. So we have a +1 and now a -1. So the bonding electrons are not being shared now due to a drastic difference in electronegativities. So they all like to bond. It's just a question of how they do it because of this idea of electronegativity or desire of electrons. And that's all coupled with ionization energy and electron affinity that we've discussed, prior. So you can actually relate this in terms of an actual equation. So a dipole moment is known as mu. And mu is essentially equal to Q times R. So here is our dipole moment. We have Q, which is going to be, charge. For instance, Q of an electron is equal to 1.6 times 10 to the negative 19th coulombs. And then we have R, which would be the distance or bond distance, separating the two elements. So if we were looking at, a pure, plus, minus, or pure ionic system, right? Mu would be equal to Q times R. Q is our charge, and R is our distance, which is, in terms of an ionic system, is roughly 130 picometers, or let's put that in correct terms, 130 times 10 to the 12th meters. So when we do that calculation, we get a dipole moment for a completely ionic system to be 2.1 times 10 to negative 29th coulomb meters. Now we tend to use a different unit. We tend to use dBi, or capital D, for our dipole moment. And 1 dBi is equal to 3.34 times 10 to the negative 30th coulomb meters. So often we do this conversion to then get to our unit of dBi in terms of dipole moment. And this is equal to 6.2. And this is for, like I was saying above, a pure ionic bond. would have this mu because of the fact that we're just talking about, the charge of that electron or a proton. Dipole moments for bonds, or rather for specific bonds, can be found in tables. So you can basically compare the dipole moment of a bond to an ionic bond. To determine the bond's ionic character. If greater than 50% ionic, you have an ionic bond. As opposed to a covalent, or as opposed to, a polarized covalent. So with our example of, say, a tellurium oxygen bond has a dipole moment equal to 3.5 Dipes. Is it covalent or ionic? And so you would just plug that in to, really a percentage. And in this case, we get 56% ionic. Tellurium oxide is an ionic bond in this fabricated example. So what I'm just trying to get across is that, these bonds that we're talking about are all different layering of electronegativities. The more similar those electronegativities are, then we're talking about sharing of electrons, not necessarily always equal, but sharing. And then you get to more drastic differences in those electronegativities. Now you find ionic systems, but it's a layering effect. It's not just pure one and pure the other, as this equation shows. The other relationship we want to get into is bond length and bond strength. And these are just some trends I want us to kind of understand. Single bond is basically, the longest. Triple bond is the shortest. And if we, kind of flip it in terms of energy or strength, we find the trend goes the other direction, with the triple bond being the strongest and the single bond being the weakest. So there's a correlation there, meaning, the shorter the bond, the stronger the bond. The more electronegative The elements are participating. The shorter and stronger the bond. So we have that electronegativity kind of at work there. So if we look at, for instance, a series here is a quick chart of, a couple different bonds. This is just a series of halides going down from fluorine to iodine, all bound to nitrogen. And if we look at our bond lengths, we have 139 picometers and an energy of 272 kilojoules per mole for our NF bond. So here we have bond length, and here we have bond strength. We get to chlorine. Now we find that that bond is actually a little bit longer. We can rationale that by chlorine being less electronegative than fluorine, but also rationalize it by that chlorine is actually bigger than fluorine, so it can't get as close to the nitrogen either. And we find that as we increase that distance, our bond strength starts to decrease as well. And so as we go down this series, we find that we have a continual decrease in those energies. So there's that relationship that we have, that we see at the top, right? That the shorter the bond, stronger the bond, right? The more electronegative the elements, again, the shorter, the stronger the bond. So that's the deal with, looking at simple covalent structures and getting a little bit more into the bonding scenario. In our next lecture, we'll now start to up the ante in terms of structures. Get into some of the exceptions of Lewis dot, and get more into elements that can do more than one thing. And we'll get into that in the subsequent lecture.